Hello students, now in this video we are going to see the speed control of our 3-phase induction motor. So far we are done with starting methods of 3-phase induction motor. Okay, how can we start? By using auto transformer starter, direct online starter, star delta starter. Okay, so those are the starters. Now let us see how to control the speed of our 3-phase induction motor. Okay, so you already know that the speed of our 3-phase induction motor is a constant speed machine, right? Our 3-phase induction motor is a constant speed machine. So we know that the speed control of DC machines is very good with good efficiency, but in order to control the speed of our 3-phase induction motor, we have to compromise efficiency of our machine, and there will be a low power factor if you want to control the speed. So let us see how can we control the speed of our 3-phase induction motor. Okay, so we know that the speed of induction motor, the rotor speed of 3-phase induction motor can be given as with NR, which is equal to NS into 1 minus S. That means in order to control the speed of our induction motor, we can control it by changing the synchronous speed or by changing the slip. Okay, let us see what are the controls that we can control using slip control methods. Okay, so we know that slip can be controlled. Okay, so slip control methods, first one is voltage control method, supply voltage control method, supply voltage control method. Okay, and the second one is rotor resistance control method, because we know that our torque expression is proportional to S times E2 square R2 by R2 square plus SX2 whole square. So we know this. So you can, if you can control voltage and resistance, so that you can control the slip. By controlling the slip and making the torque constant, you can change the speed of the machine. So that is the idea. So by E2 is nothing but our, you can make it S V1 square R2 by R2 square plus SX2 square. So if you can control the supply voltage, you can control the torque, you can control the speed of the machine. Okay, that is the idea. So voltage, supply voltage control and rotor resistance control. Okay, these two are the two methods that we can control using the slip. Okay, so let us see another control method, that is rotor EMF injection. Okay, by injecting some EMF into rotor EMF injection method. Okay, you know that these two methods can be possible in only slip ring induction motor. Rotor resistance control method, that means by adding some resistance to rotor, that is possible in slip ring induction motor, and rotor EMF injection is also possible in slip ring induction motor. So these are possible in slip ring induction motor. Okay, these three are the slip control methods. Now let us see synchronous speed control methods. As our speed of the rotor is also dependent on synchronous speed, let us see what are the other parameters that we can vary to change the speed of our machine. Okay, so synchronous speed control methods. So what are they? So we know that our synchronous speed NS is equal to 120 into F by P. So we know that the speed of the synchronous speed of the machine 120 F by P, right? So how can we change the speed of synchronous speed? By changing the frequency is one, that means frequency control, frequency by frequency changing method. Another is pole changing method, and the third one is by cascading two machines, by cascading two induction machines, we can obtain some speed control. So I will see. So here the frequency, the pole changing method, here the pole changing method is only possible in squirrel cage induction motor, because the number of poles in slip ring induction motor are fixed. We cannot change once they are manufactured. Okay, so the pole changing method is possible in squirrel cage induction motor, because the squirrel cage induction motor's rotor will be induced same number of stator poles. So the number of poles on the stator will be induced on the rotor. If you want to induce two poles on the rotor, you can make stator as two poles, so that our rotor will be induced with two poles. So pole changing method is possible with squirrel cage induction motor. Okay, and this also be classified as stator control methods and rotor control methods. So we know that our voltage control method is a stator control method, and frequency control method is also stator control method, and pole changing also a stator control method. So these three are the stator side control methods, and the rest are the rotor side control methods. Okay, let us see one by one. First one is voltage control method. And one more thing, all these methods, the speed methods, there are two types of drives here. One is constant torque drive, that means torque should be constant irrespective of the speed, that means it should supply load, constant load, that means irrespective of the load, irrespective of the speed, torque should be constant. This is one type of drive, that is constant torque drive. Another type of drive is, and we know that our power is proportional to, equal to speed into our torque T. Speed is nothing but 2 pi N by 60 into T. Okay, so our power is proportional to speed and torque. Okay, so if you want to keep the power equal to constant, so N and T should be equal to constant. So that is possible if N is inversely proportional to T. Okay, so this is another type of method. Okay, now let us see, this is constant power drive. That means N and T are inversely proportional. This is N, this is T. So P N inversely proportional to T here, and power is constant. Okay, this type of drive is called constant torque drive, and this type of drive is called constant power drive. And we will be having this type of drives or this type of drives or combined type of drives in the upcoming speed controls. Okay, let us start the first voltage control method. So I am going to consider a supply voltage of 400 volts. So I am going to consider a machine having supply voltage of 400 volts and synchronous speed of 1000 rpm and our rotor speed as 900 rpm. So I want to reduce the voltage to 300 volts. Okay, so I want to find the new speed of the machine. Okay, what is the new speed of the machine? So I have reduced this voltage, supply voltage to 300 volts. Now let me find out the new speed of the machine in rpm. Okay, so we know that, so for a constant drive, this is for a constant, for constant torque. Okay, this is important. So this condition is important for constant torque. So we know that torque is proportional to S times V1 square. Okay, so torque is proportional to S times V1 square. So in order to make torque is constant, so our S times V1 square will be constant. Okay, so I can write it from the expression S1 V1 square equal to S2 V2 square. Can I write like this? As they are constant, S1 V1 square should be equal to S2 V2 square because they are constant. So I am going to apply the values here. So S1 will be, what is the S1? Slip under this condition, S equal to 1000 rpm by 900 by 1000. So slip will be how much? 100, 100 by 1000, right? 100 by 1000. That will be 0.1. Slip will be 0.1 here. Okay, so here from expression 1, S1 is 0.1 and voltage is 400 V1 whole square equal to S2 is unknown and voltage V2 is 300 volts. Okay, so you can find out the slip here S2. So what is the value of slip here? That will be 400 by 300 whole square into 0.1. So this is my new slip. So I can find out the speed. So that will become NR equal to NS is constant for both the machines. This is slip 2. This is my NR2. Okay, this is my NR2. This is NR1. This is NR2. This is V1, V2. Okay, NS is constant. So I can find out NR2, the rotor speed. Rotor speed for a reduced voltage of 300 volts. Okay, so initially it was 400. For 400 volts, the speed of the machine is 900. Okay, now let us see what is the speed of the machine for 300 volts. Okay, so let us see. That will become NS is 1000 and 1 minus slip is 0. And what is the value? 400 by 300 whole square into 0.1. So you can find out the value. Okay, so that value should be less than 900 rpm. So that is the idea. Okay, now let us see. Okay, now let us see speed control of induction motor. The first method is voltage control method. Stator side voltage control, supply voltage control method. I can say supply voltage control method. Okay, so we know that our supply voltage cannot be increased beyond the rating, because if the voltage of the machine increases, it will destroy the insulation of the material. Okay, as the windings is having insulation, if the more the voltage, the insulation will be collapsed. So that's why we are not supposed to increase the voltage beyond its rated value, so that we can reduce the voltage. So here S2 will be equal to 0.178. So if you can substitute the value of 0.178, what will be the value? That will be around 1000 into 0. It is around 822, I think. Okay, so you can substitute, it is around 822. It is around 822 rpm. You can see the speed initially it was 900 rpm. Now it is 822 rpm. That means speed has been reduced. 80 rpm has been reduced from here to here. As we are reduced 100 rpm, 100 voltage from 400 to 300, the speed has been reduced from 900 to 800. So this is speed control by voltage control method. Okay, but this method is easiest and cheapest, still rarely used, because large change in supply voltage is required for relatively small change in speed. That means for a small change in speed, we have to change the large number of voltage, as it is V1 square. Okay, for a small change in torque, we have to change large amount of voltage. That is one disadvantage here. And another one is large change in supply voltage will result in large change in flux density. Okay, as we change the voltage, the flux density will become different. Okay, so as we are changing the high amount of voltage, the flux density will be large. That's why this method is rarely used. Okay, this is about supply voltage. So let us see from torque equation of induction motor, which is T is torque, okay, 3 by omega is, which is nothing but 180 by 2 pi ns into SE2 square R2 and R2 by, so we know, you know the torque expression, right? I think you know that. Okay, so let us see for a smaller values of slip, as our speed of the induction motor is at a full speed, let us say at a full load speed, the slip will be very small. Okay, you know that as speed of the machine is running at full speed, the slip will be very small. Okay, for a small value of slip, S times E2 square value will be very less. Okay, S times slip times 0.02, let us say consider, into something and whole square, this value will be very small considered to the value of resistance R2. So R2 value, which is rotor resistance, okay, rotor resistance is more compared to SE2 square value. So I am going to neglect this SX2 term, so that this will be the new torque expression without SX2 term. Now we know that our E2 is rotor induced EMF, that is proportional to our supply voltage V1. So I can write the expression T torque is proportional to S V1 square R2, and you know that our resistance is constant. So our torque proportional to S times V1 square here. This is important. Our torque of the induction motor is proportional to slip times supply voltage square. So now if I want to change the supply voltage, let us say I want to reduce the supply voltage. Okay, so what will happen? And I need our torque of the machine should be constant. Okay, that the machine should drive a constant torque machine. Okay, the machine should drive a constant load. That means I have to keep this torque constant. So what will happen? My torque is constant and I am going to reduce the voltage here. So in order to make this torque constant, as our voltage is increasing, our voltage is decreasing, our slip will increase. Okay, that is the thing. If the supply voltage is reduced, developed torque will be reduced. Okay, but for providing the same load torque, this is important. For providing same load torque means torque should be constant here. So in order to make torque constant, our slip will increase. As our V1 is decreasing, in order to make our torque constant, slip will increase. Okay, and as slip will increase, our induction motor's rotor speed will reduce. So this is the idea. As this value increases, this whole fraction will be less compared to previous one, and the speed of the machine will increase. Okay, I hope you understand. The speed of the rotor is indirectly reduced by reducing the supply voltage. If supply voltage is reducing, in order to keep the torque constant, our slip will increase. As slip is increasing, our speed of the machine decreases. As our speed of the machine is inversely proportional to slip. Okay, you know that. Okay, as slip is increasing, our speed of the machine reduces, so that we can obtain speed control. So this is one method of speed control. Now let us take one example.